Good afternoon, Professor.
Hello, hello. Good afternoon. Wow, awesome. That's so fast. Good afternoon. Right as my board was disappearing, I caught it. Good afternoon. I think that, well, good afternoon, Amy, for sure. I heard that. I think I heard, and so fast. That was awesome. All right, good afternoon. I'm going to do the chat because I'm not sure, but good afternoon, Amy. Good afternoon, Caitlin. Good afternoon. And Caitlin's been here since 1967. I am aware of that. Good after. I mean, you know, like for a long. Oh, good afternoon, Amanda. Good afternoon, Kevin. Good afternoon, Shamil. Good afternoon, Alicia. Good afternoon, Amanda. Hi, Christina. Good afternoon, Caitlin. Good afternoon, Jamalette. Good afternoon, Kevin L. Good afternoon, Felicia M. Good afternoon, David, who that might have been. Then I heard a second, I'm not sure. David P, I mean. Good afternoon, Chloe. Good. Why am I confused suddenly? Oh, yes. Good afternoon, Shamil. Good afternoon, David K. Or maybe it was David K. Anyway, all right. Hello, hello. Good to see you all. My board just disappeared as usual because that's like the new thing. Hold on. There it is. Okay. Okay. Oh, and more people are here. I still don't have them. This is not a surprise. I still don't have them. I'm just going to move on. You'll get them as quickly as possible. I still feel terrible. I feel as terrible as Monday, if not a little bit more, except this isn't as big a surprise because there was no way once I didn't have the Monday, there was no way I was going to be able to get, oh, there goes my board again. All right. Anyway, that's a sign. I'm going to go do some physics and then it's going to be Thanksgiving soon. And by the way, it does not escape me that for most normal people in the world, today is like already Thanksgiving, and only at John Jay do we always go straight to the last minute. That's always the way it is at John Jay. I've never understood it, but it's definitely noted that you are here, all of you, like David, Amy, Caitlin, Amanda, Christina, Alicia, Jamalette, David, Kevin, Felicia, Shamil, Chloe, Elda. It's very noted that you are here, like when you could be preparing for Thanksgiving or going somewhere or being somewhere else, and many of your colleagues already are. I totally appreciate that you're here. So I'm going to make it worth it, I think, by doing some serious physics. Okay, I don't know if that's good or bad, but that's what we're going to do. Okay, there's the board again, and obviously stop me at any time. But yes, I know how hard it is to pay attention today, but we will pay attention. I'm just getting ready. Okay, what we're gonna do, and again, by the way, there's no new homework, partly because it's Thanksgiving. Like, don't do any homework over Thanksgiving unless you have anything to catch up on. But also, I'm not giving you any new assignment until I get back your exams. I mean, that's the least I could do. Whatever. If you have other stuff to catch up on, please do. But anyway, all right. So what are we doing today? We're continuing with these diagrams. Yesterday, and I know it's a little bit dry, whatever, I'm going to stop apologizing. It's a little bit dry, but it's super important, and it makes, I don't know, it's like the heart of physics. And these diagrams are not sketches, and they're not sketchy. They're not like approximate, rough, give you an idea. These diagrams actually ultimately do math for us. Like, they are precise. They're like architectural diagrams. I mean, they're precise. All right. Anyway, so what we did Monday, right? We did system schemas for 3 different scenarios: for free falling, for an object hanging by a string, and for an object sliding along a rough surface. 3 different scenarios meant to give you one that had 1 force, one that had 2 forces, one that had 3 forces. From there, in principle, we could go on to I could give you the most complicated scenario, or for example, a lab scenario, like a rough inclined plane or something like that. And no matter how many forces and things are happening, in principle, you now have all the rules and procedure you need to make a system schema of an arbitrarily complicated situation. And because you would follow the rules that we said, Monday. And the reason you would do a system schema is that when you were done with your system schema, just following the rules of saying, okay, I'm going to put planet Earth in there, and then I'm going to put every single object that is in any way touching the mass in question, right? If you did a system schema of some mass, no matter how complicated its situation was, you would draw Earth, definitely, and then you would draw a solid circle for any and every single object in the world that was touching your mass in any way. Oh, no problem, no problem. Thank you, no problem. Thank you. So then you would draw a solid circle for every single, and hello, for every single mass that was touching, making physical contact with your object, your mass in any way. And then you would take this planet Earth solid circle and all these other solid circles, and you would connect them all with lines to your mass, right? And you would, and what you would do is you would draw one line for every one of those objects. And you would realize that each one of those lines represents a touch, with two exceptions. One exception would be that planet Earth would get a line even though planet Earth is not touching your object. And that's why you always draw planet Earth first before you forget it, because it's always there even though it's not touching, right? And then you would draw all these other objects that are touching, and you would scan them all, and for every single one you would draw one line, except you would then say to yourself, wait, are any of these objects that I've drawn, any of these solid circles that I've drawn to represent objects, are any of them a surface that is pushing against the surface of my mass, right? And when I say, are any of them a surface, I mean, like, is any of them or is any of them a two-dimensional, like, area that is flat against some two-dimensional bounding area of my, good afternoon, good to see you. Awesome. You would ask yourself, and 1 second, see, oh, thank you very much. It's just perfectly sorry about your thing. So you would ask yourself, are any of these objects, do any of these objects contain a surface that is flat pushing against the surface of my object? Like, if one of those objects is a string, there goes my board, you would say, no, a string is not a surface pressing against my object. A string is like a line pulling against my object. But for any of them that is a surface pushing against the bounding surface of your object, such as a tabletop pushing against like the outside of your eraser, then you would say, okay, for that surface, I'm going to give two lines instead of one, right? I'm just summarizing what we did Monday. And you would give it two lines instead of one, because our belief that when surfaces press against each other, they actually create two forces of interaction. They actually interact along two axes at the same time. One axis that's perpendicular to the plane of contact. Like, so right now with my hands going like this, if this is the plane of contact, they are pressing along an axis perpendicular to that, or pressing like this, and we call that the normal force. But by doing so, since these surfaces are rough, since microscopically they contain ridges and nooks and crannies that are locking into each other, they also automatically create a rubbing or sliding resistance along the axis parallel to the plane of contact. And we call that associated rubbing or sliding resistance force, we call that friction, right? So summary, and then we're going to move on. Summary, and then I'm going to put the board back on. What is the deal with this board? So summary of everything we did Monday is that you follow these rules to create this picture, and they are rules. They are so that there's no ambiguity as to what is a force or what is not a force acting on a mass. Because again, in fact, that's the hardest question really in physics, unless you know this procedure, is like, what is a force and what's not? And the answer is a force acting on an object is planet Earth plus anything and everything that's touching your object. But then right before you finish your diagram, you realize that if any of the things touching your object is a surface pressing on it, then you give that two lines instead of one. And then you sit back and you look at your picture, and the whole point of your picture, and then we're going to move on with this. We're going to use these pictures now. The whole point of your picture is when you're done, if you follow the rules correctly, then every line that you see in your picture represents a force that now we're going to turn into an arrow vector and place into a free body diagram that we're now going to together, once my board comes back on, we're going to make. So we make the system schema to figure out what are the forces. How many are there? What are they? We see the forces by seeing the line segments in our system schema. Now, every line segment in the system schema will become an arrow, a vector, in what we're now going to make called a pure free body diagram. And when I say every, I mean it literally. I mean, like if you have 4 lines in your system schema, then you better find exactly 4 arrows in your free body diagram. Okay. So now we're going to make a pure free body diagram. And by the way, if it's not already evident, we're going to do the same 3 scenarios that we did on Monday, only with free body diagrams, not system schemas. But first, we're going to get the board back on. And yeah, okay, good afternoon. Okay, I'm just getting the board back on. And it's weird. Oh, so if I enable closed caption, then I see it. But if one of you enables it, then only you see it. I didn't realize it was like that, because supposedly somebody enabled closed caption, which is totally fine. I think it's a great idea. So I said yes, but I don't see it. So I don't know if maybe that's just, hopefully whoever you are that enabled closed caption, like I'm all for it. I think that's great, but I hope it's working. Maybe direct chat me if it's not working, because I don't see any evidence of it on my side, but okay. I mean, if you're good, I'm good. Let me get the board back working. Why is this board? I'm going to try one more. If the board fails one more time, then we're going to get, then I'm going to have to discipline the board. I'm going to have to speak to the board's parents. Okay, here comes the board. I think, oh, chat. Oh, this chat is about to close caption. Oh, it is working. Okay, thank you. So, but it's not on my side. Okay, good. Well, if it's and by the way, if any of you find the closed caption disturbing or distracting, tell me that too. Like, I don't mean it to be like a, but I just assume if someone wants it, then I assume that's a good thing. But oh, I do. No, I don't see. Okay, no, but good. Thank you, direct chat people. Okay, here we go. Here we go. Okay, the double yabber. Okay, so here we go. Here we go. Okay, so okay, I'm going to read this out loud quickly because of my handwriting, and then I'm going to try to explain. There's more to come, more instructions to come. But again, just like yesterday, just like Monday, I'm giving you the general instructions, directions of how to draw a free body diagram. it's a very classic old physics skill. You may have seen it in high school. You may have seen them in high school. I mean, system schemas are a little bit more modern, to be honest. You may never have seen, it's possible many of you sort of recognize a free body diagram, but have never heard of a system schema. System schemas were developed later, more recently, kind of like in your lifetime, actually, they were developed, or certainly in my lifetime. Free body diagrams are more classic. And again, I'm aware that already in lab, probably you've been asked to draw free body diagrams. And I'm very aware that you can look up both of these things on the web and get instructions, stuff like that. The instructions on the web can be helpful. They can also be confusing. There can be some debate over styles about how to do these things. Of course, there's some style, but I will tell you that I'm pretty confident if you follow my directions exactly, you certainly, I'm not saying it's the only way, but I think my directions, I think they'll leave no room for what am I trying to say? I'm trying to say, when in doubt, follow my directions. I think they cover all cases, is what I'm saying. Like, you won't have to think if you follow my directions. And if they conflict with anything you found on the web, bring it to my attention. I mean, if it's confusing, bring it to my attention. But or if they definitely, if any of my directions about either of these diagrams conflict with anything your lab instructor has said, oh, then definitely let's work that out. But okay, so these instructions are in general how to draw a free body diagram. I'm going to apply these directions one case at a time to the 3 cases for Monday. But first of all, you start with, we're looking at all the forces acting on a given mass, a particular mass whose acceleration we ultimately want to compute. So now we're going to start by drawing a dot at the center of our page. It was a dotted circle for the system schema. That's for system schema. There's reasons for that. But in the free body diagram, we just draw a dot. Again, some web pages will do it differently. Fine, but I think there's good reasons. And I think the classic way is to draw a dot. And the dot represents a point in, oh, sorry, I should just read the handwriting. It says, draw a dot on your page representing the center point of your mass at one point in time. Okay, so even if your mass is a big baseball, or your mass is a plant, or whatever you're looking at, or a cup of coffee, you pick sort of what we ultimately in physics call the center of mass. You pick sort of the representative central location of that object, and you remind yourself that you're going to picture that one point of mass at one point in space at one point in time. So the reason we draw a dot is now we're going to like really focus our attention on just that one point of mass at one point in space and one point in time. And we're going to look at all the forces acting on that one point. This is going to start forcing us to focus and to realize that this is the way the forces act. They act on one point in space at one point in a time. Okay. So then instruction 2 says, for each and every line segment in your SS, in your system schema, draw an arrow emerging from your point. Okay, so that's what we're going to do. In other words, for every line segment in your system schema is going to turn into an arrow. In this diagram, the tail of the arrow is going to start at your point. Again, sometimes some web pages do this differently, but I think then it gets very confusing, and I think it becomes confusing. Start every arrow with its tail at your point and have the tip come out of your point. Okay. Furthermore, to A. Okay, I'm going to read this out loud. Give me a second. Something else just happened. Okay, so what it says. Okay, so it says, I'm just reading the words. 2A, each arrow should point in the direction toward which the force is pulling or pushing your mass. And 2B says the length of each arrow should approximately, in parentheses, qualitatively, comma, comparatively represent the magnitude of the force. Now, let me explain this for a moment. Again, we're going to do this together, of course, but 2A and 2B are saying that each one of these arrows that you're going to put in your diagram is a vector. It has direction and it has magnitude. So A is about the direction, B is about the magnitude. Now, about they each have a sort of subtlety associated with them. Maybe I should go in the opposite. Well, the direction, this is subtle. The direction is super important. In fact, sorry, I keep getting interrupted because of life. You should never view interruptions as interruptions. You should view them. No, I shouldn't say you. I should never view interruptions as interruptions. I should view them as opportunities to expand the repertoire of my soul. Okay. Direction, a little bit subtle. You're going to see this when we're making the pictures. First of all, it's really important. The first thing I want to say about direction, the fact that we've converted these line segments into arrows is because the purpose of the free body diagram is to start recognizing, analyzing, mathematically using direction. Like, direction's really important. All of this is to generate the math. Please remember, all of this is to set up the math. The math will do the computation that will get us the answers we're looking for. But please remember that many of us at one time or another have said about physics, I can do it, I just don't know how to start it. And what we really mean by that is I can do the math, but I don't know how to initiate the physics, which is also ironic because everybody thinks the scary part of everybody thinks the scary part of physics is the math, but it turns out actually math is actually the crutch of physics. The hard part of physics is actually the physics. And so the whole purpose of these diagrams is to do the physics for you. Honestly, if you're still with me, if you're still paying attention, a lot of you, this whole diagram thing, as much as I don't know why I keep defending it because I'm a defensive guy, but it may all seem very dry and weird. But the truth is, this is the thing that you never got in the first chapter of physics, like, because we just didn't have it to give you. Like, if you're looking for like a procedure to get you off the ground and then know how to run your procedures, this is it. Like, it's the diagrams, okay? But so the purpose of the free body diagram is to construct these arrows that are ultimately going to tell us what directions things are happening in, which is ultimately going to tell us which axis to apply each of the three F net equals MA to, and which is ultimately going to tell us where the pluses and the minus signs go. So direction is like huge to do the math. So the first purpose of the free body diagram is to take the lines of the system schema and turn them into arrows. Now the arrows have to point in the direction that the force points. This is a little bit subtle. I'm saying, for example, when we do free fall, when an object is being pulled toward Earth, that means Earth is pulling down on the object, on the mass. The Earth is pulling the mass down, so our arrow will point down. I mean, that might sound obvious in that case. Hopefully it does. But remember that case. It all sort of comes back to free fall. Whenever there's a force happening, you draw the arrow in the direction that the force is trying to push or pull your actual object. Okay, like that's number one. And so we're going to do that in a minute. Then number two, you try to make every arrow have a length that approximately represents the magnitude of that force. But I have to be careful about that because look, if you literally knew the magnitude of the force right from the get-go, you wouldn't need all these pictures and everything. Like the reality, so this is something that gets people legitimately confused. We don't literally know the magnitude of a lot of these forces until we do all our calculations. So it's understood that you can't specifically make the lengths perfect. Like you literally can't. But what we're saying is take each arrow and give it as your best prediction, your best rough idea of how big or small that force is compared to the other forces in the problem. And so in other words, try to make your arrows have sizes that comparatively indicate what's going on in a rough sense. Okay, so that's not a precise thing. That is a rough thing. But so direction of the arrow, length of the arrow. Okay, that's those two instructions. We're just about done, I think. Hang on. Wait, there's one other instruction to give you. Yes. Okay, yeah, and then finally, this is minor enough. I'm just going to keep it on this page to see. Okay, so finally, instruction C, which is the last instruction, it says on the side, it says label 2C, label each arrow with symbols, not numbers. Okay. Symbols generally will mean like letters or words. Like in other words, if one of the arrows represents the normal force, we're going to write out normal. So I could say symbols or names, but not numbers. This is just to encourage you that the arrows are going to enable us to do calculations. But if you start doing the calculations in advance or thinking you know the answers to the calculations in advance, you're going to go in, you possibly are going to go in circles or double psych yourself. So we try not to put numbers on the arrows. We try to put names or symbols on the arrows. And you'll see. Okay. So these are the rules, and that's it. So we're going to take the lines of our system schema and we're going to turn them into arrows. This is to make a pure free body diagram. There's yet one more type of diagram after that, but this is what we're about to do. What was that? Just to note, maybe you could write this down somewhere. The purpose of this free body diagram is now to start getting directions straight. You might ask, well, what was the purpose of the system schema then? Because notice the system schema does not care about direction. In the system schema, like I drew Earth wherever. I didn't draw it up or down. I just put it wherever. And I put the string of the fishing line wherever. The system schema was not at all concerned with direction. What the system schema was concerned with identifying the actual objects that are generating these forces onto our mass. It's to force us to realize that if you're looking for what forces are acting on your mass, the only way to find them is to first look for any and every other actual object in the world that's interacting with your mass. The system schema is to force us to realize that forces are mutual interactions between pairs of objects. It's to prevent us from making up forces that don't exist, which people tend to do otherwise. So in the system schema, we've got these blocky objects like solid circles and dotted circles that are like showing us, oh, objects are interacting in the world, okay? And then they generate these lines, which are the forces. Now the lines are these abstract things. The lines are not objects, right? The lines are these forces, which we're now going to mathematically analyze, but we're just really trying to remind ourselves that they didn't come from nowhere. They came from somewhere. But now that we've got them from our system schema, we put them into the free body diagram, and you'll notice when I start drawing them now all those solid circles and those dotted circles disappear. We no longer care about those objects anymore. We're just going to care about our mass now. Okay, so the system schema emphasized the original interacting objects that gave us the interactions. Now we abstract from that and we trust ourselves and we look at just the interactions themselves. So, example 1, Freefall. Hang on. Okay, example 1, Freefall. So I draw my little dot that represents the mass. If you even like, I could put a little M next to it, which means mass, but it's always the mass, so you don't really have to do that. And I look back at my system schema from 2 days ago. You look back at your system schema from 2 days ago. If I try to turn the pages, everything's going to crash, of course, on this end. And I look at my system schema from 2 days ago, and I remember, okay, I had my little mass in a dotted circle, and I had over here planet Earth in a solid circle, and there was one line connecting the two, and that's all that the two circles, and that's all that was going on. There was just that one force, that one interaction with Earth, because by definition, that's all that's happening in free fall. So I take that one line and I turn it into an arrow here, and I emanate it from my point mass. Like I start the tail at my point mass, and now I care about direction. So planet Earth pulls my point mass down if it's in free fall. By the way, even if the mass is velocitizing up, it's still being pulled and accelerated down. So I draw an arrow going down, okay? And then I'm going to label that arrow with the name of the force itself. We said 2 days ago that the force of pulling that comes from planet Earth, we often call gravity or gravitation, but we also have another word for that, which is worth getting used to. And that word is weight. So I can write weight there. That's my pure free body diagram, essentially. I mean, that is my free body diagram. But now I'm going to make a modification. Now I'm going to use it for the first time. Like, what do I do with this free body diagram? Why do I care about free fall so much? I care about free fall because it's the simplest example, but also because it's the example that has Earth acting, and Earth always acts. In all of my other examples are all built from free fall because every other example has weight in it. So let me stop and think, let's analyze. We're going to use this diagram now to stop and solve F net equals MA. Remember, please, that's always ultimately the purpose of these diagrams, is to solve F net equals MA. Often, we're going to have to first go to what's called a vector component diagram to solve often. But if the diagram is super simple like this, I don't even have to do that. You'll see it's not even going to change anything. So I'm going to stop for a minute and actually show you how to use this diagram in order to apply and solve for Newton's second law. Okay. So I'm about to show you one quick, simple practice of how you use the diagram to solve for F net equals MA. Usually, as I've mentioned many times, usually we're making all these diagrams so that we know what all the F's are to all add up and put into the left side of F net equals MA and thereby solve for A. That's what we're usually doing. Here, the thing is, this is free fall. We already know what A is for free fall. A is G, if you know what I mean. Like A is like 9.8 meters per second squared. Or if we're on the moon, it's 1.16 meters per second squared or whatever. We know what A is. It's the acceleration due to free fall. So actually here, I'm actually going to plug what I already know to be A in and see if I can infer or realize anything about the F's. So I'm going to say this. Like I plugged in my 1/4. So what do? I plug in, I look at my diagram, and every arrow that's in a particular axis. In fact, sorry, I skipped a step in effect. Hold on, I'm sorry. Okay, I'm showing you the procedure. So just to be clear, F net equals MA is a vector equation. It really means that independently but simultaneously along each axis, net F equals MA. So it means like the sum of all the Y forces equals the acceleration in the Y direction, while independently but simultaneously the sum of all the X forces equals the acceleration in the X direction, et cetera, et cetera. Like that's what it means in general. And in general, whenever I'm solving complicated problems, I'm going to do one Newton's law equation for each axis. Now, here in this case, there's only one force. It's only acting on one axis. Like nothing's happening on the x-axis, right? So I'm going to go straight to the y-axis. And I'm going to now plug in all the forces I see on the y-axis. I'm going to plug all the forces I see on the y-axis into the left side. If some were going one way and others were going another way, then I would give pluses and minus signs, right? But there's only one here. So I'm just writing it in. Weight is the one force I see in the y-axis. Apparently that equals m times a along the y-axis. Like this is how you do the procedure. But we know in this case that ay, the acceleration along the y-axis, equals g, like we just said that a minute ago. So in this one case of free fall, I'm going kind of in the backwards direction. Instead of using all my F's to get an A, I'm actually using my pre-knowledge of A in order to realize something about the F's. What I just realized, it's kind of just a vocabulary thing, but what I just realized is that the weight of any object is its mass times the acceleration due to gravity. Like the force with which the Earth pulls any object is the mass of that object in kilograms times 9.8 meters per second squared. I just use the well, here, so I'll write on Okay, just to be clear, from now, I'm saying there's three different things now that are all related to gravity. There's mass, there's the acceleration due to gravity, and there's weight. We just used an example of something free falling because it's the simplest example to discover things. We used the case where the only thing acting on an object was its weight to realize that the weight of an object is its mass, measured in kilograms, times the free fall acceleration due to gravity, measured in meters per second squared. In other words, we just used the case of free fall. We just pictured a 1 kilogram object falling toward Earth, realized an object falling toward Earth, which is pulled to Earth by its own weight, would fall at a rate of 9.81 approximately meters per second squared. So what we just realized was that the force, since F net equals ma, and the only F on the object was its weight, we just realized that the weight of the object was the weight of the 1 kilogram object is 1 kilogram of mass times 9.8 meters per second squared of acceleration. The weight of a 1 kilogram mass is approximately 9.81 newtons. The weight of a 2 kilogram mass is like, 38.2 newtons. And I want to emphasize maybe three things about that. Number one, we use the example of free fall, but it's still true. Even if a 1 kilogram mass is sitting on a table, which is kind of like our next example, or hanging from a fish line, its weight is still that. It may not be so a 1 kilogram mass has a weight of 9.81 newtons, even if it's not falling at 9.81 meters per second squared, right? That's what I'm trying to say. Like, this is the relationship between your mass is how much should I write this down? You may want to write this down. I'm afraid to get myself bogged down. I want to go to the next example, but you may want to write this down. The mass of an object is how much it resists changes in its motion. Mass is resistance to acceleration. Your mass is how much you don't want to be accelerated. Meaning, if I say that my brother, who's an FDNY, is twice as massive as me, what I mean by that is if you pushed us each with the same force, I would accelerate at twice the rate as he would. You know what I mean? Like I'd go flying, he wouldn't. Or put another way, if you wanted my brother and me to if you want to shove my brother and me, and my brother's bigger than I am, okay? He's not literally twice my mass, but let's just say my brother is twice my mass. If you wanted to push each one of us and get us to accelerate the same rate, you want to get us up each to the same speed in the same amount of time, you'd have to push my brother twice as much as me. That's what it means. Like F net equals ma. M is the constant of proportionality between F and A. Your mass is inversely proportional to the rate at which you accelerate given a certain force. So mass is just resistance to force in general. I mean, it's resistance to acceleration when you're subject to forces. That's what mass is. Weight is a particular force. My weight is how much the earth is pulling me down. Right? So mass is measured in kilograms. Weight is just a force. All forces are measured in newtons. They're two different ideas, very different ideas. One is like a cause. The other is more like a resistance to an effect or something. One goes on the left side of F net equals ma. The other goes on the right side of F net equals ma. Because we all live on Earth, there's a simple conversion factor between the two. The conversion factor is 9.8, is G. But okay, from now on, lowercase g stands for the acceleration in free fall due to gravity. Lowercase m stands for mass, but m times g from now on stands for weight. And I'm going to move on in a second, but I want that to be clear because from now on, in every single diagram we ever draw, whether something's free falling or not, when I say like in the system schema, you first draw the earth always in the system schema, from now on, same point, in every free body diagram, the first thing you do is you draw a downward arrow that we're going to label mg. from now on. And that downward arrow is the weight of an object. Every single object that has mass automatically is pulled toward Earth and has its own weight. That is a force on it. That force might be balanced by other forces, so the object might not be falling. But in every single system, free body diagram from now on, there's always a downward arrow labeled not M and not G, but mg, which means weight from now on. And this is kind of what I was saying before when I said you got to label all the arrows with symbols or words or names, but not numbers. The first classic symbol or name that I'm talking about is mg. Okay, everybody with me? I will stop being Elmo or something at any moment. All right, so with this new recognition in mind, Freefall FBD is this. So the Freefall FBD is this. One arrow pointing down that says mg on it. That is Freefall, okay? So now I'm going to move to the next example. Okay. That is Freefall, mg. But again, please remember, mg means weight. G does not mean weight, and M does not mean weight. Mg means weight. Oh, and also please understand, like newtons are the metric unit for weight, only because newtons are the metric unit for force. In America, we measure weight in pounds. Weight, like that gets really, but that's not metric. I mean, that's the imperial system or whatever. So pounds are the American equivalent of the metric unit called newtons. They're not the American counterpart to kilograms. They're the American counterpart to newtons. You can convert easily among all these things because there's an easy conversion factor from kilograms to newtons. So there's an easy conversion factor from newtons to pounds or from kilograms to pounds. But newtons and pounds measure the same thing. Kilograms do not. They measure mass. What's the American version of kilograms? Oh, that's a very good question. There is an answer, but we never use it in regular life. The American, you can look this up, the American equivalent of a kilogram is a slug. I mean, like, no joke, it's a slug. Like, no one ever used, but that's what a slug is, an imperial unit for mass. I mean, that's just the way it is. And there's similarly, well, that's it. And I will say this, when I mean, this is so stupid. I'm going to move on, but when Professor oh my God, did I just forget? Everybody's favorite chemistry, oh my God, why did I just forget your chemistry professors? Oh my God, I'm getting so old. Oh my God. What's your chemistry professor say? How? Oh my God. Wait, this is disturbing. I'm going to move on. But oh, thank you. Yes, thank you. Okay, thank you. And I was kind of, I wasn't doing that really to see if anybody was paying attention, but I kind of sort of was. Thank you, Felicia. Yes, exactly. Professor Sheehan. I don't know where my head is. Yes, Professor Sheehan, very good friend of mine. Years ago, way before COVID, when he had a grandchild, like when one of his grandchildren was born, and he sent around like an announcement, or we were all excited. I sent him a congratulatory note, but I converted, but they, when babies are born, they're always like, oh, it's 4 pounds, 3 ounces. And I sent back, for some reason, I congratulated him and converted his grandchild's mass into slugs, and because only he and I would, and he appreciated it. But all right, this is totally stupid. All right, but that's the only time in my whole life I've ever used slugs, just to make a stupid joke when a fellow science professor's child had a child. Okay. Okay, so but thank you, Felicia, for paying attention and for knowing your chemistry professor. He will be very touched. Yes. Okay. Case 2. Case 2, the fish on the line. Okay. Okay, it's 1:10, we have 20 minutes. Okay, so now we're going to do the second example, fish on the line. Slightly more complicated because now there's two forces instead of one. Right? And let's say for the purpose of this example, let's say the fish is literally hanging on that line, on that fishing line. Okay, like it could have been being pulled up or could be pulling it down, but for the moment, first, let's say it's hanging stationary. Okay, so we're going to do the free body diagram of this fish on the line. So the first thing we do is we look back to our system schema. We look back at we look back at the systems. Well, we draw a dot in the middle of the page representing the fish of mass M. Okay, there's our fish, mass M. We look at our system schema that we made on Monday. There are two lines in that system schema, right? One line that represented the pull of weight from planet Earth, and another line that represented the pull from the string, and we decided to call that other pull tension. That's the word from now on. We said whenever any one-dimensional piece of material is pulling on something, so like a string or a rope or a rod, whenever something like, as opposed to a two-dimensional surface pushing, whenever you have or as opposed to like planet Earth pulling, whenever you have like a piece of material or a wire, whenever you have a one-dimensional piece of material pulling on something, we say that the force exerted, the pulling force exerted by that material, we call it tension. Okay, so we had these two lines in our system schema, one that represented weight and one that represented tension. So each one of those lines now becomes an arrow in our free body diagram. I always do the Earth gravity weight arrow first because it's always there. And now I know that it's always going to be pointing down. And now I know that it's always called mg. That's in every single diagram. Mg, first thing you draw, right? Okay, the pull of the Earth down. In other words, the weight of the object. But now I've got this other arrow which is the line of the fish. Now, this is what I was sort of getting at before. That line, that fishing rope string is pulling up the fish, right? Like it's pulling up the fish. How do I know it's pulling the fish up? I mean, I think to many of us that may be sort of obvious, but maybe it's not. How do I know it's pulling up? Well, one thing is I know that if that line were not there, the fish would fall. So if the fish is not falling, that line must be pulling up. Another way I know is it's on top of the fish and it's a pull. Good question, chat. Oh, that's a very fair question. Felicia's like rocking and roll. It's like Felicia Day. Oh, yeah. No, that's a very, very fair question because I'm being so precise about it's actually a great question because it just goes to show you. I always forget, like I'm being so precise about some things and then other things I don't care. But how would you know what I care about and what I don't? Right. No, the truth, great. So Felicia's asking, like, where I actually write the MG, does it actually matter? And no, it does not. To me, it does not actually matter. I'm going to go with Felicia. So Felicia's suggesting maybe to go like that. And you know what? That probably is a better idea, what Felicia's saying. I don't think it's strictly changing anything, but just for keeping the diagram uncrowded, that's maybe for the rest of my life, I might actually deliberately do that. I think that's a good habit. Honestly, what Felicia's suggesting, like maybe putting the MG under the arrow or something like outside of the whole body of the diagram. Good idea. Okay, cool. Look at that. And she's even showing that she's paying attention in the lab. Okay. Oh, I'm also going to take this as a subtle suggestion that maybe I should be speeding up. Maybe I'm going too slow for some of you. Sorry, but no, great points. Definitely great points. Totally fine. Yes. Definitely not worse what you're saying and probably better what you're saying than what I'm doing. Okay, so we got the MG there. Now, okay, so now we got this other arrow representing the tension in the string, and I definitely think it goes up. Again, because if it weren't there, the whole fish would fall down. So I'm going to draw an arrow going up, and I'm going to label it with a T for tension. Now, also, okay, so I'm just about done. I think this is my diagram because there were two line segments in my system schema. You know, it's really cool too that she can pay attention even when she's probably bored because it's probably going too slow. It's so awesome. It makes me so happy. It's not awesome that she's bored. I'm not saying she's bored. Am I talking to myself? Yes, I am. Sorry to interrupt myself. Okay, but no. Anyway, But you guys always can tell me in the direct chat, like, yeah, we know, please speed up. Like, really, I wouldn't be insulted, especially not by you guys. I mean, I would cry all night, but I would handle it. Okay, so I put the arrow going up, called tension, and I'm done in a principle because I had 2 lines in the system schema and I've got 2 arrows here, so I'm done. But notice one other thing. I'm approximately sort of guessing that I think these arrows are equal in length. I'm guessing that because in my head, I'm kind of I'm guessing that they're equal. And let me verify that right now. Why am I guessing that they're equal? So just like I did before, I'm trying to get myself into the habit that the purpose of these FBDs is to solve F net equals MA. Now, again, we're on sort of simple examples here. Usually in complicated examples, like in lab, you're adding up all the F's to get an A. Here, it might be going the other direction, but which is fine too. So let's see. Well, first of all, like that means it means there's a separate, I'm just getting in the habit of saying when I write F net equals MA, there's one for every single axis. And, you know, by the way, especially since it sounds like at least one person in the room really is following what's going on in lab and all of that. This is all, lab is the complicated version of all this, of course. I mean, I know that lab, and I got to get to that. But it is the complicated version of all this. I promise you, however, even though it's the complicated version of this, it literally is this. If you really understand these procedures, then you really can apply them to lab. The 2 big missing pieces that I haven't gotten to yet to show you this with lab is I haven't broken these arrows into components yet, which I totally know that you have to do for lab. So I haven't broken them into components. That's the next step. I mean, I haven't shown you how to do that. And also I haven't gotten into the details of friction yet, which you need to know for lab. But quick question, and I really do appreciate, all joking aside, I appreciate what Felicia's saying and anybody else who's still with me. So quick question. When did your lab report already is your lab report already turned in, or when is your lab report due for lab 5, or, you know, the slowdown lab? Is it already? Do you understand what I'm asking? Well, I'll keep going, but if anybody could tell me in the chat where you are with what's due in lab, that would also help me, because I want to help you not waste your, or is there not something due? Oh, it was due. Oh, okay. I'm sorry. All right. Well, okay. All right. Well, gotcha. Okay. Well, I appreciate your honesty. Thank you, Caitlin. All right. Good information. So this may be sort of frustrating to some of you. All right. Well, this is on the final anyway, so it'll definitely help you with the final. I promise that. Okay. Well, all right. So I'm going to solve. So there's nothing happening in the x-axis. It's all in the y-axis. So just like before, I now put in all the forces into the y-axis that I got from my picture. So, and I'm labeling, like, everything that goes up in that picture, I'm going to call positive, and everything that goes down, I'm going to call negative. I mean, I could go the opposite way, but that's what I'm calling. So tension is a force. It's going up. I'm adding it to gravity. Like, I'm just writing down the 2 forces that are in my diagram, and I'm adding them up. But since gravity is going down, I'm going to call that a negative. So really, to be really clear, if I can, I'm really saying this. But that's what I add. T minus mg equals ma. I'm adding up all the forces, but I'm taking into account any minus signs. Now, just like before, it happens if assuming we were told that this mass is stationary, So A equals 0. Therefore, A equals 0. Therefore, T equals mg. In this case, like if there was anything I could solve for in this case, if there's anything I could learn, I already knew the acceleration, but from the acceleration, what I learned is that the two forces are not only opposite in direction, but they are equal in magnitude. Now, a couple of things. First, so I just learned from F net equals ma that the two forces are not only opposite in direction, but they're equal in magnitude, which is why it was sort of, so I might have even seen that in my head when I was drawing the picture. So it was wise that I made the two arrows roughly equal in size. It turns out they are precisely equal in size. I just proved that, right? But okay, so that's good. And some lab instructors and some web pages will have you even put a little like etch mark or hash mark in each of the any two arrows that you think are equal in size. That's fine if they're doing that. I don't do that, but that's cool. But here comes I know there's 9 minutes. Here's a very important subtlety that may have been confusing you in lab, and even if you already turned it in. Like I'm now saying that those two forces are equal in magnitude and opposite direction. So it raises a very legitimate question. Oh, is this what we meant by Newton's third law? Remember, in Newton's third law, we said, like, if object A pushes object B, then object B pushes object A with a force that is opposite in direction and equal in magnitude. So many people will either ask the question, oh, is this Newton's third law right here? Or more to the point, many people will just assume unconsciously or consciously that this is Newton's third law. In fact, many people will even say that it's Newton's third law. In fact, many books and web pages and some teachers who are wrong will even say that this is Newton's third law. More to the point, sometimes students will think that a teacher said that this is Newton's third law because some web page did it. What I want to be right at, but it's not. And it's really important to know this is not Newton's third law. Let me be very clear about that, even if this is the last thing I do today, which it probably will be. The answer is no. And this is really important because honestly, this is a big misunderstanding that does matter and that gets promulgated on the web. To be really honest, this is one reason it's a really bad idea to use Chegg for any of our exams. Not just because it's unethical and ridiculous, which it is, but because like they get this wrong. People get this really, and it really matters. Here's what I mean. Okay. I'm saying these two forces, tension and gravity, they are equal and opposite, but not by Newton's third law. Here's what I mean. what I'm going to do now, and this is often an exercise like on the final exam or whatever, it's a sidebar, but it's not a tangent. Like, so we're making these, and I know there's only 6 minutes left. We're making these diagrams of forces and all that, right? And we're trying to figure out their magnitudes and their directions. But Newton's third law plays a very important role in all of this. It's important to see what the role is that's played by Newton's third law. So often we will stop at any moment looking at any diagram and we'll stop and say to ourselves, I mean, when we're trying to solve a problem or in the middle of a final exam, we'll stop and say to ourselves, hang on, okay, I've got a diagram now. Let me list every instance of Newton's third law that's being generated or discussed or identified by this diagram. Newton's third law says that every push goes in 2 directions, every pull goes in 2 directions. Newton's third law absolutely does say for every action, there's an equal and opposite reaction. But the reason I never phrase the law that way is if you just say that, if you just say Newton's third law says for every action, there's an equal and opposite reaction, it's not at all clear what is the action and what's the reaction or whatever. It can mislead you into thinking something like the weight of this fish is an action and the tension in the string is a reaction. That is not the case. Here are the action. So what we do is we stop and we look at a diagram and we list every action reaction pair implied by a diagram. So I know I have 4 minutes. So I'm just going to do it now. I'm going to say it. And if I need to explain it more on Monday, I will. But here's the deal. Okay, I'm going to say right now, because I know I have 3.5 minutes. I'm saying the 2 arrows in one diagram are never the action and reaction to each other. Every arrow in an FBD is an action, and it has a reaction in some other diagram. I'll say that again. Every arrow in an FBD is an action, and it has a reaction in some other diagram that we may or may not be drawing. No arrows in a diagram are ever a reaction to any other arrow in a diagram. This is what I mean. I've got 3 minutes. I'm going to write it. What I mean is, here's the list. Here's the list that I'm looking for. 1, Earth. Well, here's 1. If I look at the MG arrow, what does it mean? It means Earth pulls down on mass. That's the action, okay? Therefore, by Newton's third law, mass pulls up on Earth. That is one action-reaction pair. If the Earth pulls the mass down, then tug-of-war, mutuality, symmetry, mutual interaction, then the mass pulls up on the Earth. That is one interaction. The Earth is pulling the mass down, the mass is pulling the Earth up. And it most certainly is. Is the Earth accelerating very heavily? No, because the Earth is really, really massive, right? The mass is pulling the Earth up with 9.8 newtons or like whatever it is. If the Earth is pulling the mass down with 9.8 newtons, then the mass is pulling the Earth up with 9.8 newtons. Do we see the Earth accelerate a lot? No, because F net equals ma. The huge M of the Earth will yield a very small a under the same F. But action-reaction pair number 1 is Earth pulls mass down, therefore mass pulls Earth up. And so no law is saying, so in other words, if the Earth pulls the mass down, there's no law that says that tension has to pull the mass up. Obviously it doesn't, because the mass can be in free fall. If there were a law that said every time I was pulled down by something, something else would have to pull me up, then no thing would ever accelerate, right? So the action-reaction pair number 1 is Earth pulls down on mass, mass pulls up on Earth. And the other pair, number 2, implied by the tension arrow, is rope or string, whatever, pulls up on mass, therefore mass pulls down on rope. Those are the two action-reaction pairs. The point is, with 1 minute left, the rope is not a reaction to Earth. If it were a reaction to Earth, that would mean every time anything is pulled down, something else would pull it up. Nothing would ever accelerate. Newton's third law is I push you, therefore you push me back. Newton's third law is never two forces on the same object. Newton's third law never describes two arrows in the same FBD. Newton's third law says that for every one arrow in an FBD, there is a matching arrow in some other FBD. That's 130. We'll leave it at, sorry, I'm yelling. Oh, what I mean to say about all of that is happy Thanksgiving. We are done. So thank you for your attention. Have a great day. Yes, yes, you too. You guys are so good. Like, you're like actually paying attention. Yes, happy Thanksgiving, all of you. Seriously. I'm sorry about your exams too. Thank you. Thank you. Have a great break. Yes, have a great break, all of you. And I'm turning this off, I promise, but I'm still here if you have a question. Thank you. No, thank you. Happy Thanksgiving. Thank you. Thank you. Thank you. Yes, have a great day. Thank you. Okie dokie. Happy Thanksgiving.